So this is section 12.4, page 820. This is infinite geometric series. And so now we're going to have a series where we're looking at the entire thing. Now here's the key, folks. These are infinite geometric series, not infinite arithmetic series. If we take an arithmetic series, something like 1, 3, 5, 7, 9, that would be the sequence, right? So the series would actually look like this. And we add this up forever, what is this going to add up to? Yeah, this is going to be no sum. We do not say that this thing is equal to infinity with the sideways 8 symbol. Okay, you guys all know the infinity symbol, right? The thing is that infinity with this symbol is not an actual number. It's actually the limit of a process, and I'll talk about that a little more in just a moment. So we can't say that something's equal to infinity that way. We can say it's infinite, but we can't use infinity as a number. That infinity is not an actual number. Okay? Not a number that we can do normal operations with. So we say that this has no sum. When we say no sum, it's not a sum that we can actually quantify because it gets bigger and bigger and bigger without boundaries. There's no number that can contain that answer. Okay? Everybody got that idea? Now what we're getting into here, when we start to talk about infinite or infinity in mathematics, we're starting to get into some very high-level concepts and some very, very deep and philosophical kinds of concepts. And to me, this is actually one of my favorite things to look at in mathematics is things involving infinities. Because they start to call into question kind of the nature of the entire universe. Okay? Unfortunately, we don't have time to go into too much depth with that. But does everybody see that there's no actual sum that we can attach to that? No number. Everybody's okay with that idea? What about a geometric series? 1 plus 2 plus 4 plus 8 plus 16 plus ... What's the sum of that going to be? Again, it's going to be no sum because it's going to approach infinity. It's going to get bigger and bigger and bigger without boundary. Okay? It turns out, though, that with geometric series, there is a situation where there actually is a way to give a sum for the series, even though we're adding an infinite number of terms to it. And so what I want to do is I want to talk to you about a very specific one. So we're adding more and more and more. They're all positive numbers. So what is this thing going to become? Yeah, this actually becomes 1. Turns out that the sum of this series approaches 1. And so we say for all intents and purposes it's equal to 1. So here's the idea. Who should we pick on today? We'll pick on Nick since he asked for extra time for his homework. All right, here's Nick. He's walking home from band practice after school or from shooting his video after school today. And here's his house. There you go. So there's his house. And he lives 1 mile from school. And he needs to walk home. But he's tired after practice. And so he can't make it all at one time. So he's only capable, after marching around the field from 3 o'clock until, whatever, 5:30, 5 o'clock, he's exhausted, and so he can only make it halfway at a time. So he's going to walk from here to here. So how far has he walked so far before he takes a break? Half a mile, right? Which leaves how much? Half a mile. So he's going to take a break, and then he's going to start walking again. But again, now he's extra tired, so he can only walk halfway again. So how far does he walk this time? A fourth of a mile. Right? And now he rests. Now he stands up, and he says, okay, I can make it halfway again. So how far does he walk this time? An eighth of a mile. And then what? And do you see that that's creating this series up here? Do you guys all see that this is a geometric series? What is R? What is our common ratio? What are we multiplying by each time? A half. Multiplying by a half. Right? A half times a half is a fourth times a half is an eighth, etc. The question is, will Nick ever get home? See, that's the issue, guys, and this is a paradox that is known as Zeno's paradox, or it's related to a paradox called Zeno's paradox. Let me talk to you for a moment about Zeno's paradox, give you guys something interesting to think about. Zeno's paradox, and there are other paradoxes like it, there are ones that involve this halfway thing, but Zeno's paradox was actually a paradox having to do with the rabbit and the hare. You guys all know the story of the race between the rabbit and the hare, right? The rabbit and the hare. The tortoise and the hare, excuse me. The rabbit and the hare are the same thing. The tortoise and the hare. So what happens in the story? Right? And who's fast? The hare. And who's slow? The tortoise. And what happens when they start running? The hare takes off and builds up a big, big lead, and then what? Yeah. The hare gets cocky and says, oh, well, I can lay down and take a nap for a while. I'm going to beat this guy anyway. And eventually, who wins? The tortoise. Well, in Zeno's paradox, he breaks it down like this. And he says, well, the hare starts running. Let's say at some point the hare reaches this point. The tortoise starts running. And by the same time, let's say he reaches this point. But at some point, if the tortoise continues, doesn't he eventually reach the point where the hare used to be? But at that time, where's the hare? He's already gone on ahead. So now the tortoise has got to catch up to the point where the hare used to be. But where's the hare now? He's further ahead. And so now let's say he's here, and then the tortoise, by the time he reaches here, the hare has already gone to here. So the question is, how can the tortoise ever possibly catch the hare? If by the time the tortoise has come to where the hare used to be, the hare has gone farther. So how can the tortoise ever even catch up, let alone win the race? But if the hare doesn't stop, now we're not talking about the story now. In the story, the hare stops, right? And that's why the hare loses. But this is not related to the result of that story. This is a situation that just involves the same two animals. But if the hare doesn't ever stop, how can the tortoise ever catch up to the hare? He can't. Even if he slows down, even if he gets tired and slows down and the tortoise doesn't, by the time he gets there, the hare has gone that far now. He's still ahead, isn't he? Right? So as the tortoise goes to catch up, the hare goes a little bit further. And so the question is, how can the tortoise ever possibly catch up? Well, isn't this the story of every single race? Now again, we're not talking about the fable of the tortoise and the hare. We're talking about this situation. You guys have all been in running races or swimming races or whatever, right? And of course, the person that gets off to the quickest start always wins the race, right? How can they not? Doesn't the slower person have to catch up to where the faster person was, and by that time, isn't the faster person farther ahead? That distance may get smaller and smaller, but isn't there always some little difference there between their positions? Do you guys see the paradox? that when you think about it logically, it doesn't seem to make actual sense, right? It goes against your intuition. Your intuition tells you that the slower runner can eventually pass the person who gets off to the faster start. Right? If they start to run faster and the other person starts to run slower, they can eventually catch him. But if you think about it in terms of just position, even if this guy is running faster and this guy is running slower, there's still going to be maybe a smaller and smaller gap, but isn't there always going to be at least a little bit of a gap? And it turns out that, yes, that is absolutely true if these objects are points with no size. That's the way I view this thing. Just like our situation with poor tired Nick trying to get home. If Nick has no size, if he's actually a point with no dimension, he's going to get closer and closer and closer and closer and closer and closer to his front door, but he's never going to reach his front door, is he? Because there's always going to be half of the remaining distance left. But the reality is he's not a point. He does have size, and eventually what's going to happen with his shoe? It's going to open his front door, right? He's too big to fit into that gap that's left, and he will reach home. Does that make sense? So thinking about it in terms of position of a bouncing point with no dimension is different than an object in the real world that actually has size. Okay? And at some point, if you have a runner that's speeding up and a runner that's slowing down, or just one or the other, it doesn't necessarily have to be both, right? That lead is going to shrink to the point where it's so small that the slower one actually catches the faster one. And once they're in the same position, then whichever one is running faster is now going to start to build a lead. And the one who started out slower will eventually pass the one that started out quicker. Does that make more sense now? But do you guys see the paradox if you're just using it as an exercise in thought and you're not taking into account the size of the objects involved? You can see where this kind of confusion or this kind of issue arises. And there are a lot of different paradoxes in mathematics. Okay, have you guys ever heard about the Barber of Seville paradox? So there's a barber in a town called Seville in Spain, and the barber shaves every man in town who does not shave himself. The barber shaves everyone who does not shave himself. So the question is, does the barber shave himself? Who shaves the barber? Well, he only shaves himself if he doesn't shave himself. If he doesn't shave himself, how can he shave himself? What it is, guys, is it becomes circular reasoning. Okay, and that's the source of a lot of these paradoxes in mathematics. But you could spend years studying all the different paradoxes in mathematics. And a lot of them are very, very deep. These are relatively simple ones. Okay, so I just want to give you guys some interesting background on the problem. But let's go back to our results. Since Nick does have size, and he's not just a bouncing, point, like a flea, only smaller. He does have some size. Eventually, as tired as he is, it may take him a long time, but eventually his shoe is going to hit his front door and open his front door, right? And so he's going to make it home. So the question is, how far did he travel altogether? 1 mile. He made it from school to home, 1 mile. So 1/2 plus 1/8 plus 1/16 plus, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, etc., on and on forever. If you add up the entire series, it essentially equals 1. Now, the question of whether it actually equals 1 or not is a huge debate, or at least was a huge, huge debate among mathematicians. I'd say it still is to some extent. And it brings up an idea in mathematics called the limit. The limit of a process basically says, what is this thing equal to within some boundary, within some threshold? Okay? So I could say, how close does he have to get to that 1 mile before it's close enough to consider it a mile? Does he have to be an inch away? Does he have to be 1/10 of an inch? If he's 1/1,000,000th of an inch away from his front door, has he essentially walked a mile? What about 1,000,000,000th? What about 10,000,000,000th? What about 1,000,000,000th of a mile? What about 1,000,000,000th of an inch? Well, if you were a trillionth of an inch away from something, wouldn't any reasonable observer looking at you say that you're standing on that object? You couldn't even see a trillionth of an inch. So the question is, how close is close enough for us to consider it 1 mile? Well, whatever answer you come up with, I can get you closer still. How do I get you closer still? I just go a few extra terms. So if you want to get half a mile away, I just need the first one. Right? I can get you even closer by adding the next couple of terms. If you want to be a trillionth of a mile away, I just need to go out until you're a trillionth of a mile, and then just add another couple of extra terms, and you're even closer still. Actually, technically, I only have to add one extra term. So do you guys get that idea? So that's the idea of a limit. So basically, we're saying that it approaches a value for all intents and purposes, because as close as you want me to get, I can get closer still. Do you guys understand that idea? Because this is an idea that's going to become extremely important in calculus. Because when you guys deal with limits in calculus, what you're really doing is you're starting to build up a foundation for dealing with derivatives and for integrals, which are extremely useful real-world mathematics. Okay, the technology that we have today all around us would not exist without calculus, which would not exist without the concept of limits. So don't think that these limit things are just something that somebody made up. These are absolutely real. And we have the proof all around us. We're standing in it, we're sitting in it, we're sitting on it, we've got it in our pockets, we've got it in our homes, we've got it in our cars, everywhere. All technology, for the most part, is related in some way, shape, or form to this concept. So it is very real. Okay. So what we've seen now is that there are some geometric, infinite geometric series that have a sum and some that don't have a sum. The question is, how do we know whether we get a sum or don't get a sum? Well, take a look at these two series that we were looking at. We had 1 plus 2 plus 4 plus ... We had 1/2 plus 1/4 plus 1/8 plus ... This one was no sum. This one was equal to 1. Why were we able to find the answer to one of those but not the other? It's not about fractions, although you're on the right track. You've got to be careful, guys, because I could write 117 over 2. That's a fraction, right? But if I add 117 over 2 over and over and over, aren't I going to get a bigger and bigger and bigger sum forever without any boundary? Yes, ma'am. I'm sorry? Whole numbers and like how the bottom line is in all whole numbers, the other one. Well, I mean, again, these are whole numbers too. And again, if the top number is bigger than the bottom number, it doesn't matter if the bottom one's a whole number. But if we start to put some of these ideas together, you guys are zeroing in on what we really care about. What's that? That's the idea. What were you going to say, Sabrina? Okay. That's the idea, guys. The difference between these is the size of what we're multiplying by each time. It's the size of R. It turns out that if the absolute value of R is less than 1, why the absolute value? Because we could be multiplying by -1/2 as well. So if we did 1/2 and then -1/4 and then +1/8 and then -1/16, that would also, it wouldn't give us a 1, but that would also give us an actual sum. The idea is if R is less than 1, there is a sum. I should say there is a finite sum. There's a sum we can actually attach an actual real number to. So this is extremely important. I can't stress this enough, guys. I am about to show you a formula that will calculate the sum of these things for you. Because we're not going to be able to just look at things as easy as this and say, oh, look, that's going to add up to 1. You know, put Nick however far away from his house and see how far he travels. Can't do that with every just generic kind of infinite geometric series. So I'm going to show you a formula. Here's the problem, guys. The formula only gives you the right answer if the absolute value of R is less than 1. In other words, if our r is essentially between 1 and -1. So another way to think about this is to say that -1 is less than r is less than 1. If that's the case, we can find the sum using the formula. The problem is, if r is not in that range, the formula will still give you an answer, but it will be wrong 100% of the time because there is no finite sum. So you have to decide whether you're allowed to use the formula or not. The formula will not tell you, oh, nope, sorry, I don't work on this one. The formula is going to tell you, sure, I work on this one. The answer is 17. Right? Too bad you're adding things like -1, -2, -3, -4, -5. Right? You've got to get a negative answer, and the formula tells you the answer is positive 17. And there wasn't a single positive number anywhere in the series. Okay? So, you have to pay attention to this condition. Everybody clear on that? If you pay attention to this condition, these are actually the easiest problems in the chapter. So let me give you an example. Let's look at something we haven't looked at before. Have you guys ever seen anything as crazy as this in your lives before? We want to find what the sum of that infinite geometric series is. What is r? 1/2. Is it between -1 and 1? So we can use our formula. What is our formula? Well, remember that we had an S sub n formula for adding up the first n terms? Well, now we're just going to have an S formula because we're adding up all of the terms, the whole series. And it turns out that it's equal to A1 times 1 minus r to the n over 1 minus r. So much simpler than the one we used in the last section, right? Oh, wait, that's the same formula. Let's think about this for a minute, guys. R is between 1 and -1. R is a fraction less than 1. When I start raising a fraction like 1/2 to a power, that becomes 1/8. Is that bigger or smaller than 1/2? Smaller. It's getting smaller, right? What happens if I raise 1/2 to the 30th power? Smaller still, right? Pretty darn small. Right? 1/2 to the 10th power is 1 over 1024. What happens if I raise it to this power? Would you guys say that that becomes pretty tiny? What does it essentially become equal to? Don't you guys agree that that's essentially 0? It becomes so close to 0 we can't even tell the difference between that number and 0. So here's what's going on, guys. R is not getting closer to 0. R to the nth power is becoming 0. What is 1 minus 0? 1. What is a sub 1 times 1? Here is our formula for infinite geometric series. The 1 minus r to the n approaches 1 in its limit, and so it basically disappears, and we just get the first term over 1 minus r. Didn't I tell you that the infinite one is actually simpler than the non-infinite one? Because that messy term that gave us headaches in the last section disappears in this section. So now if we want the sum of this particular series, it's going to be the first term, which is 1/2, divided by 1 minus r, which is 1/2. That's 1/2 divided by 1/2, but we don't divide by fractions. What do? Which is equal to what? That's where the 1 comes from. Do you guys see how that works? Let's try another one. Okay. What's our r here? 1/3. Is that between -1 and 1? Yes. Give it a smiley face. So, S is equal to A1 over 1 minus R. That's 1 divided by, what's 1 minus a third? 2/3, but we don't divide by fractions, so we multiply by the reciprocal. This series is going to equal 3 over 2, 1.5. Do you guys see how easy the formula is to work with? Yes, you have to multiply by the reciprocal of the fraction on the bottom if you end up with a fraction, which you will. That's it. That's the hardest part of the whole formula. But the trickiest part of the whole formula what's R here? So the sum is equal to 1 over 1 minus 4/3, which is 1 over negative a third, multiplied by the reciprocal. What is this equal to? -3. So clearly, a positive number plus a positive number plus a positive number plus an infinite number of positive numbers can somehow magically give you a negative answer, right? You guys all buy that, right? So the problem is, guys, that R was not in the right range. You have to stop and check this. This one gives us a sad face. So you don't do this. If R is not between 1 and -1, you put what? No sum and you're done. But again, did the formula tell us that we were doing something wrong? The formula gives you an answer and says, sure, I work. The formula lies. What's that? Math? What math is what? Like your wife? Non-existent? Oh. Is that what that was? Oh, that was a burn right there. Okay. Any questions about how that works, guys? There's nothing hard about this formula, but what's tricky about the formula is you have to remember to run that test on R. That's it. If you remember to run that test, these should be the easiest problems on the test. But guess which are going to be some of the ones that you guys miss the most? Why? Because you guys don't check for R. Now, one last thing I want to point out to you, and then I'll answer any questions. They don't have to write it like this. The 1/2 plus 1/4 plus 1/8 plus ... doesn't have to be written like this. It can also be written like this. Do you guys see that's the same series? When you plug in a 1 for I, what do you get? A half. When you plug in a 2 for I, what do you get? When you plug in a 3 for I, what do you get? On and on to infinity. Now, how do you know when you're being asked to find the sum of an infinite series? Well, they're either going to ask you, it's going to say dot plus ... and it's going to ask you to find the sum of the infinite series, or it's going to have an infinity on the top of the summation. That's how you know they're asking you to do the whole series and not just part of it. That's it. Any questions? Going once? Going twice? Okay, homework.